Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey, Houston, we don't have a problem. In fact, the fact that we're in Houston is sort of pivotal in Mr. Bergmann's life. When I was a young lad in 1969, I was born in 1964, I was 5 years old, my parents rented a motel room, and in the middle of the night, we watched...
On this July 20th, 1969.
That's one small step for man, one giant leap for mankind.
It was a pivotal moment in the history of America and really the world when the lander landed on the moon. But then something more intriguing happened. The astronauts did something crazy. This is what they did.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Wait a second. You're telling me that a feather drops at the same rate as a rock? That's exactly true. Crazy, isn't it? So a bowling ball and a feather, they land at the same time. But that's not your experience on the Earth, is it? Probably not. But a very, very famous experiment conducted by Galileo. And it is in theory where he did it at the Leaning Tower of Pisa. Not pizza, but Pisa. And he discovered that two objects, when they fell of different masses, they landed at the same time. Crazy! But true. And what he discovered is that the acceleration of gravity, okay, we could say that, well, let's say this, two objects, regardless of their mass, fall towards the Earth at the same acceleration. And we have a particular acceleration here on the Earth. The acceleration due to gravity, big important number is the acceleration of gravity, if you will, is 9.8 meters per second squared. In fact, we don't even usually call it A. We just say little g is 9.8 meters per second squared. Now that's here on the Earth. Because gravity, of course, as you probably recall, is the attraction of one body for another, it's going to change. The acceleration of gravity will change on different planetary bodies. On the moon, it wasn't as large because the moon is less massive. So I don't know what the numbers on the moon, but it's just a smaller number. It's not 9.8. And here's actually another interesting thing. Is actually g changes with your change in elevation to some degree, right? So, you know, we got the Earth right here, but some parts of the Earth are mountains. And at the top of the mountain, because it has to do with how far you are from the center of the Earth. And of course, at the top of the mountain, you're at a different place. So the value of g gets smaller the further you are away from the center of mass. Now, at the top of Mount Everest, maybe it's 9.79. So it's not much difference than it would be. So this is free fall. This is an amazing thing. And as you know, we did this in class, but it's so cool and awesome. So yeah, near the surface of the Earth, it's 9.8 meters per second squared. And as we just saw, astronauts confirmed this by dropping them on the moon. So when we do these problems, all right, we've got a couple of problems we want to do that are called free fall, acceleration due to gravity problems. Let's take a look at these. These are just applications of the same set of equations that we've been doing before. So we've got a pair of sunglasses falling from the hot air balloon, okay. They're 225 meters above the ground. All right, so boom, they're going to fall 225 meters. Draw on a picture, right? Okay. If the air resistance is negligible, calculate how long does it take for for them to reach the ground? Now let's make a note here. The acceleration, because it's on the Earth, is equal to, actually we'll say negative 9.8 meters per second squared, because of course they're falling. If we make the downward direction negative, that's typically the way we like to do this. And that's all we know. Of course, I'm trying to find the time, or delta t. So which equation do I want to use? So if you've got your equation sheet, hopefully you realize the equation we're going to use is delta d is equal to v initial delta t plus 1/2 at squared. But the initial velocity is 0, so vi equals 0. So this term is 0. So we can say delta d is equal to 1/2 times 9.8. That's it. Actually, we can not change that a. Let's just call that g, if you will, t squared, and times t squared. And delta d, we're going to plug that in. Sorry, that's going to be 225. So let me get this out here. Calculator. I'll take 9.8. Well, I can do that in my head. 9.8 divided by 2 is 4.9. So I can say 225 is equal to 4.9 t squared. Divide both sides by 4.9. So 225, oops, got a clear calculator, 225 divided by 4.9 equals. Now how do we get t? So that's this, so I get 45.9 is equal to t squared. Actually, we could still leave it as, not going to have negative. We can leave it as positive, because if we can define the positive direction as going down, usually we'll reverse. Anyways, how do I solve for t? Square root of both sides. Square root of t squared is t, so t equals the square root of 45.9. So I'm just going to take the square root of the second answer on my calculator, and I get 6.7 seconds. So if you drop something off of something, we can actually calculate how long it will take to fall to the ground. How cool and awesome is that? All right, what's the final velocity before they hit the ground? So we have a second question right here. So we have the same given parameters. Now, what a question am I going to be looking for? If you think about it, in this second question, I'm trying to find v2, right? So the question we're going to use now, the equation, pardon me, is going to be, now again, I'm just jumping out here, but you should be referring back to your notes and stuff. v2 squared equals vi squared, v1 squared. Sometimes I say I, by the way, because it means initial. Some people, I learned it initial and final, but I think it's easier to do 1 and 2. All right, plus 2a delta d. All right, so we're going to find this. Of course, the v initial, or v1, is 0, so v2 squared equals 0 plus 2 times 9.8 times d. And d is, what was it, 225. So get my calculator out here so I can say 2 times 9.8 times 225 gives me a big number, 4410, and that's equal to v2 squared. And of course I'll just take the square root of that, and I get v2 to be 66.4 meters per second. Make sense? All right, these are really pretty easy problems. They are simple problems based upon what we've been learning more and more. All right, let's do the tennis player question. She's tossing the ball up in the air. All right, this is a little different question. All right, so you've got the tennis player, right? But she's going to toss it up. All right, and this distance here is 1.2 meters, right? And she's giving it a velocity, an initial v1, equal to 3.6 meters per second. Now, this is actually important that we figure out what we're going to define as positive and negative. So we're going to say positive is up. All right, but what's also coming down is it's accelerating down at 9.8 meters per second squared. That's g, right? So these are the initial things, and we're trying to figure out how high does the ball go up when you throw it up in the air. So again, we're trying to solve for what? Delta D. All right, and so we know all of our variables. So which equation are we going to use? We're going to use, again, this equation, V2 squared, you'll see how this works, equals V1 squared plus 2a delta D. Now, what's going to be true when the ball reaches the top? Its final velocity, if you think about this for a moment, will be 0. Right, because it's going to go up in the air, woo, stop, and then come back down. So at the very top, his velocity is 0. So we actually know that V2 is equal to 0. And now we're trying to solve for delta D. Now delta D would rise above the 1.2. We'll have to add 1.2 to it, but let's get to that. So I can say 0 equals the initial velocity, so it's 3.6, right, squared, plus 2, now this is important, times negative 9.8, right, because we're defining downward as the acceleration of gravity, downward is the negative direction, times delta D. And we're trying to solve for delta D, right? And so get the calculator out, right? 3.6 squared is 12.96. We'll just call that 13. So 13, I'm going to see if you realize this is a negative multiply, so I can add both sides and just put it on the other side. So that'd be 4.9 delta D, because I subtracted it and multiplied it at the same time and brought it over to this side. Divide both sides by 4.9. So 13, I've got that on the calculator, divided by 4.9 gives me 2.64. So delta D equals 2.64. Now that's meters above the spot right here. So actually, the actual height will be 2.64 plus 1.2 meters. So that's 3.84 meters. Makes sense? Again, this is just an application of what we've been learning. All right, B, how long does it take for the tennis ball to hit the ground? This is just like the problem we did in the last exercise, because once it's at the top, at the height of 3.84 meters, it will just fall to the ground, right? So once we know that it's traveling at 3.84, we're trying to find delta T. Now actually, let me think about that. I may be wrong about this. That's how long it's going to take to fall to the ground to get from the top. But we've also got to calculate how long it took to here. So we need to determine T here and then T for the fall. So it's like two separate problems. All right, so that's important. So let me think this through. What equation am I going to use? I'm going to use the equation, delta D is equal to V1 delta T plus 1/2 AT squared. Let's just say G, T squared, where G is the acceleration of gravity. So delta D, this is how we would do this. Delta D, we can do this in one equation. Delta D is going to be negative 1.2 meters, because he's going to fall 1.2 meters overall. But his initial velocity in the upward direction is 3.6. We know our time. Oh no, we're trying to find time. Plus, and this will be negative 1/2 times 9.8 times t squared. Now this is going to be a little bit more complex mathematically, but we're smart people, right? So I'm going to, you know what, I'm going to simplify this on the next page because I think we need some more space. So then what I'm going to do is this will come out to negative 1.2 equals 3.6 times t. It's really technically delta t, that's all right, plus negative 4.9 t squared. Now this became mathematically a little bit more complex, didn't it? Because now we have a t squared and a t. I don't know if you realized it, but we've just been introduced to quadratic. Remember quadratic formulas and all that kind of stuff? So I have to set this all equal to 0. I can say negative 4.9 t squared. I've set it equal to 0 if that recall. This is hopefully ringing bells, equals 3.66 t plus 1.2. So that's how I would set that up. And this, if you recall back to quadratic formula, this is a and this is b and c. And if you recall, the quadratic formula is negative b plus or minus. All right. The square root of b squared minus 4ac over 2a. And I'm not going to belabor how to solve the quadratic formula. I'm going to assume you know how to do that. I would plug in a, b, and c. And I would get two answers, by the way, right? Quadratic gives you two answers. So delta t is going to be either negative 0.25 seconds or delta t is equal to positive 0.098 seconds. Now let's think about this for a moment. Which is the correct answer? Now only one of them makes sense from a scientific physics-y perspective. You can't have negative time, right? So the answer is 0.098 seconds. Make sense? No, 0.098, pardon me. I did it, 0.98 seconds. So this is the only one that makes sense. I thought that was too short. So about a second, if she throws it up, 3.6 meters per second to go all the way back and down. So don't panic if you see a quadratic. It's not so hard. You've done this before. B squared minus 4ac divided by 2a gives you the answer. So hopefully you guys get this free fall. It's really awesome, and you guys are awesome. We'll see you in class. Hoorah!
Okay, Houston, we've had a problem here. This is Houston. Say again, please.
Houston, we've had a problem.